Welcome to our lecture on state diagrams. We're going to we talked about interaction diagrams last day, which is one of the two main kinds of diagrams for representing the behavior of objects and systems. Today we're going to talk about state diagrams, which is another approach, complementary approach to representing behavior of systems. You can represent the behavior of an entire system, or part of a system, or an individual object. And later on, we will see, in fact, how you can represent the behavior of an individual object. Okay? So what we say is that at any given point in time, okay, a system or object is in a given state. Every object is always in a certain state, and it's in that state until it changes state. An object will change state when one of its instance variables changes, okay? And it's in a different state, because in that different state, certain methods will do different things. They will respond differently. They will give different answers. Okay? A system is in a certain state when it will respond in a certain way. When the system changes state, it will respond in a different way. Okay? What causes things to change state are called events. Okay? So an event might be say a system driven by user interface, mouse clicks, button presses, things like that. In a client-server system, it might be the receipt of a message. Okay. We can also think of parts of systems changing state. So, for example, a particular connection to client might have a state of how it's connected to the client, whether it's got the password yet, whether it has authenticated the client yet, etc. Okay. So the system as a whole could be in a state of accepting messages, and a particular connection could be in a state of being authenticated or not being authenticated, and a particular object could be in a state as well. Okay? State diagrams are graphs where we show the states as the nodes of the graph and the transitions between states triggered by events as the arcs linking those states together. Okay? So it's directed because we're going from one state to another. And we'll see plenty of examples in a few minutes. Our first example, Tic-tac-toe game, also known in some parts of the English-speaking world, such as where I come from, as Noughts and crosses. Okay, this is a game which has basically two main states. But let's take a look at the syntax first. The black circle means this is the starting point. Okay, so whenever you start the system, you're always going to immediately jump to wherever the black circle is pointing to. So we have an arrow pointing from the black circle to X-turn state. That means that at the beginning of tic-tac-toe, noughts and crosses, it's X's turn to play. And so the game is in that state. Okay? It's not O's turn to play, it is X's turn to play. What happens then? Well, we can have a transition. There's in fact three possible transitions from X-turn state. There's an arrow going down to O-turn, there's an arrow going to X-win, and there's an arrow going to tie. But which state occurs depends on various conditions. Obviously, at the beginning of the game, the first time you're in X-turn state, it's not possible to go to X-win or tie. There have to be 3 X's in a row to go to win, and it's impossible to get any in a row for a tie to occur. So there will be conditions written on these. We'll see conditions later. So generally speaking, what would happen is you go X-turn, O-turn, now you're in O-turn state. Now different things occur. The O player is the one who's capable of making moves, and the X player is not able to make moves. Okay, so the system will accept different inputs at this point. It will accept the O player moving and clicking on a square, presumably. And it will move backwards and forwards between X-turn and O-turn until one of the conditions leading to one of the terminating states takes place. Terminating states shown here as these little target symbols. Easy to remember which is which. The start state is a black dot, but the end state is a target shape, okay? As in a bow and arrow target. You can see the little black dot with a circle around it. I guess they have more rings than that, but at least it's got one ring around it. Okay? And so in this case we have 3 possible ending states, and the system is considered to have stopped running when it reaches any of these terminating states. Okay. So this is relatively straightforward. I told you the other day that state diagrams have quite a bit of power, analytic power, and we'll see that later on. Okay. the concept, generally speaking, is relatively straightforward, so hopefully you understand what's going on here. Any questions? Okay. So a few things about states that we need to remember then to make sure that we get the concept of state straight. At any given point in time, the system is in one state. Okay, now we will see later on that you can divide a system into subsystems, and we consider each of those a system, and so you can have parallel states. But for the purposes of a diagram you're drawing, okay, these simple diagrams are drawing right now, you're in one state at a time. You go backwards and forwards, and you move around the diagram. Okay? And it will remain in the state until an event occurs. The event will take it from that state to one of the other states to which it has an outgoing transition. It has to have an outgoing arrow from the current state to some other state in order to make that transition. Talked about the state having a rounded rectangle and the special states, the start state and the end or terminating state. Okay? A transition, which is a change of state, is considered to occur instantaneously. Okay, so the idea is that a variable assignment or a button press, there is a point in time when that event occurs and you're immediately considered to be in the next state. Clearly the computations involved in changing state can take some time, but from the mathematical perspective in modeling states, we don't consider that period of time to be relevant to any of our analysis because nothing can interrupt it. Okay? In one point you're in one state and things can happen, events can occur, and we just abstract away any time it takes to transition from one state to the next. The next thing that occurs once you've transitioned is something that will take you from the next state to somewhere else. Okay? So we just abstract away any time differences between states. The state transition occurs instantaneously. And we can label the transitions to say what causes the change of state. In the previous tic-tac-toe diagram we didn't show that because it was relatively obvious, but we will in fact want to start labeling these things. Fell off here. Moving around too much. Slide 24 has two diagrams, diagrams of traffic signals with various kinds of transitions. Just take a look at the one on the left. Okay, we have green light, yellow light, red light. Whenever you're analyzing a state diagram, you look at the starting state. Okay, so we start at red light. I guess it makes sense that if you're turning on traffic lights for the first time, that they be red, stop the traffic, and start the orderly progression of things. Okay? Now, the transition that goes out of red light, and there is only one, is after 30 seconds. This is a piece of UML. It's a way you write the label on the state where you want to transition after a period of time. So the event that causes this transition is a timeout event. And that takes you to green light state. Okay, so the only thing you can do from red light state is go to green light state. And it'll happen automatically, okay, after 30 seconds. There's nothing to stop that. And then after 25 seconds, it'll go to yellow light, and after 5 seconds back to red light, and round and round and round forever. Okay, so nothing will cause this system to get out of this sequence of red, green, yellow. There's no terminating state here at all. Okay, very simple, somewhat degenerate state diagram, but it is a diagram that does make logical sense, and it's valid UML syntax. Let's take a look at the one on the right. We've added a few details here. On the right, we again are modeling traffic lights, and we again go to red light state. After 30 seconds, we again go to green light. But this says green light, no trigger. Okay? What this is it's a special light, okay, that is designed to allow traffic to turn a corner. Normally speaking, we're going to stay in green light, no trigger until we get the event vehicle waiting to turn. Okay, so if we imagine an intersection or something where we have, this is the center line, and then this is the traffic going the other way. We'll think North American here. Maybe we've got traffic that can go straight here and traffic that can turn here. Okay. And so there will be a light here that's controlling the turning going this way. A little arrow going there, okay? And this line, this light here is one of the things. But this says green light, no trigger. What this is doing, I guess, is instead, right now it's saying that we're going to be green light until traffic is waiting to turn. So I guess what's going on here is not this diagram, but rather a diagram that looks something like this. We've got traffic waiting to turn here, and this is the light that we're interested in here is the one that's here, okay? So this will stay green, letting traffic flow until we have some kind of, I know, let's make it go that way, until we have some kind of traffic waiting here on a signal, triggering a signal, okay, and wanting to get into the flow. There's a good diagram for that in the book, okay? I'll let you take a look at that. These diagrams both come right out of the book, and you can actually see pictures where I've illustrated intersections in the book. The point is that when traffic wants to cut across or turn across your flow, you want it to block the traffic that is in the way. And so when we have this signal, and this is now not a timeout event, it's some kind of an event triggered by a mechanical device. Vehicle's waiting there, it picks up the magnetic signature of the vehicle. Okay, it says green light change triggered. It's going to wait for a little while now. Okay, it says after 25 seconds since exit from red light state. Okay, so we have to have this green light for at least 25 seconds. Okay, so if traffic keeps showing up here, it's not going to suddenly trigger a change and stop this traffic. This traffic is going to get at least 25 seconds of flow. Okay, even if traffic is waiting here. If no traffic is waiting here, we stay in green light, no trigger. As soon as traffic comes here, we move into green light, change triggered. Okay, and now this traffic is still flowing, but its days are numbered. Okay, it will eventually be given the yellow light, and then red light, and at red light time, presumably, there is a corresponding traffic light here that will let the traffic turn. Okay, this one here will go green when this one goes red. Is the concept. The important thing to note on this diagram is the way I've shown the notations. The vehicle waiting to turn, the mechanical signal, the after 25 seconds since exit. This is a way you write this kind of thing in UML. Okay, precisely like this. Okay, time since exit from is a key word. Red light. Okay, red light being a state name. Okay, so if you want to make sure that the transition only happens after a certain amount of time, since a certain thing happened, this is the way to show it. And again, we have after 5 seconds, after 30 seconds of simple timeouts, as before. Question?
Why is it 25 seconds from the red light state? Because isn't it 25 seconds from the green line trigger?
That's another way of doing it. What he's saying is, why do we say after 25 seconds since exit from red light state? Why don't we say 25 seconds from green light being triggered? That will be another possibility. What I'm saying here is that if a car shows up immediately upon let's say that this light here has been green, so this has been red for a long time. Okay. What would happen with this system is that as soon as I get here, I would immediately jump. Vehicle waiting to turn, green light change triggered, immediately jump to yellow light. So I would immediately, after 25 seconds, as long as traffic's been flowing for 25 seconds, any car showing up here would immediately cause trigger to yellow. That's the way this diagram says. That is one alternative. You're suggesting a different design alternative, which says, as soon as I show up here, I start a time count for 25 seconds. That is a different design.
Yeah, but it's from what it's saying, to me, it's 25 seconds from the...
No, you're explaining a different design. Okay, my design behaves one way. My design says, as soon as the car shows up here, okay, if traffic's been flowing for more than 25 seconds, it will immediately trigger change to yellow. Okay, that is my design. My design explicitly says since exit from red light state. Okay, your design is different. Your design says after 25 seconds since green light change triggered, or in fact just after 25 seconds, you could put there. That's a different design. That's a perfectly fine design, maybe even a better design. Okay? Okay? That design is saying, when we get here, we wait 25 seconds, and then we will be able to go. Okay? It's a different design, though. You have to understand the difference. Okay? Think about it. Yeah?
Why is it that you have after 30 seconds you leave the red light, and then you have another after 25 seconds since red light? That does it?
Okay. The idea is that once the light does become red, it will stay red for 30 seconds, guaranteed. Okay. This will stay red for 30 seconds to guarantee to let these guys go for 30 seconds. And then it will go up to green light, no trigger. In which case, it's waiting. It's waiting to see what will happen. What you're saying is, why don't we just go directly from red light to green light, no trigger? Is that what you're saying?
Well, what I'm saying is, after 25 seconds, it's always going to be true because you're waiting 30 seconds before getting.
Oh yeah. You're absolutely right. After 25 seconds, it's exit from red light state. After 30 seconds, it's always going to be true.
25 seconds after the newest thing.
Yeah, right. The point is that I'm in red light state for 30 seconds. That's what this is saying. Okay. Once I've exited from there, okay, I start this 25-second timer. Okay, that's the difference.
Another question: if there is no vehicle waiting to turn, then there has to be a timeout in the operating state.
No, if there's no vehicle waiting to turn, this light will stay green forever. This light will stay red forever. Okay? In other words, we're only going to, this is one of those things where we only actually change the light if a car is actually waiting there. Okay, otherwise it just sticks there forever. You're right. In different kind of intersection, you have different rules. Each intersection has its own rules. This is just one design. Okay? Here's another diagram, another state diagram. We're adding more and more pieces of notation to this as we go on. Okay, this has what we call conditional transitions. Let's follow it through. We start in planned state. Okay, now this is a diagram, by the way, of the states of a student, of a course section object. Should say it in the title. It's a course section diagram, okay? Okay, so we start in the planned state. The course section is planned to be offered. Okay, at some point we open registration. So we don't open registration right away. We maybe wait until a certain period of time, maybe 5 months before or 6 months before. Okay, because we want to do an orderly process. So there's an open registration event. Presumably a method call on the object that causes an object, a variable to be set that says you can now accept registrations. So we're now in the state open, not enough students. Okay, so this implies that this is open for registration, but we can't teach it yet because we've got to have some students before we teach it. Now, out of open, not enough students, there are 3 possible transitions. So 3 possible things can occur, and we will do whichever one occurs first. Okay, we have cancel. Okay, if somebody presses cancel the course, it will get cancelled. In fact, there's 4 outgoing transitions. Close registration. If somebody says close registration, we're not going to accept any more students. Fine, that can occur too. We go to the cancel state, because if we don't have enough students and we close registration, well, it's effectively the same thing as canceling. It's just a different event. Somebody pressed a different button, but it has the same effect. Okay. So notice here we've got 2 transitions going from open, not enough students to cancel. We have a reflexive transition, request to register. Okay, an event occurring, request to register, a student is the argument, and now we see some notation. / create registration. After the / is an action. So what happens on this action is we're going to create a registration. Call the method, effectively, if this is just a straightforward code where everything's implemented in one object as methods. Okay, so that will go on. We can do many of those. We can cancel at any point. We can close at any point. At some time, class size greater than or equal to minimum occurs. Okay, this is the occurrence of this condition becoming true. Okay, now we've seen conditions before shown in square brackets. We'll see that square bracket notation later on. Okay, when we show a condition, which you can tell because it's got a Boolean operator in it and it evaluates to true or false, when you see a condition that doesn't have square brackets around it, it means it's evaluated every time anything happens, and it will cause the transition by itself whenever it becomes true. Okay, so when the class size becomes greater than or equal to the minimum, we move into open enough students state. Okay, so open enough students state says now we have enough students to run the course. We're going to offer the course. And its behavior is a little bit different of the object in this state, okay? Because now, if we close registration, okay, we don't go to cancel, we go to closed. Because before, if we close registration, we go to cancelled. Now, if we close it, we go to closed. So it's different. Behavior is different in each. The whole idea behind us being in a state is that the behavior will be different if you're in a different state. And this is the key piece of behavior that is different. Another piece of behavior that is different is class size greater than or equal to maximum. If we get to the maximum number of students we can accept in the course, we'll also go to closed automatically. Okay? Whereas closed registration is something that is done by a human being or by another part of the system, a button press or some kind of timing mechanism. A signal is sent to close registration. Class size greater than or equal to maximum is a condition that is automatically triggers the change of state and is evaluated every time anything happens in the state. So the state diagram itself will automatically cause a transition to closed here. Okay, cancel will take us to cancelled no matter what. Keep the students out, that's fine. And we still have this ability to request to register. And that just keeps us in this state. Adding new registrations as we go on. Of course, eventually we'll trigger the change, class size greater than or equal to maximum, will trigger the change to closed. Okay, some questions?
As soon as the class size is maximum, we will go to the closed state, right?
Yes.
So when will it ever test for class size greater than maximum?
Okay, his question was, as soon as class size is maximum, we'll go to the closed state, so why do we bother to say greater than or equal to? Why don't we just say equal to? Very good point. This is a safety mechanism, okay? It's a bug prevention mechanism. Generally speaking, if you have, anywhere in software engineering, if you have a condition where you want to guarantee that something will happen upon a value being equal to, but the same thing ought to happen, basically, wouldn't happen if it's less than, and should happen if it's at that value, and obviously higher than that value could never be got to. It's safest to put greater than or equal to. Just in case a bug occurs and you accidentally get the larger value, it forces you over to the closed state anyway. Okay, so it's just safer. You're right. Logically, this would never be needed, but there's no harm in putting greater than or equal to, and it reinforces the concept when people read the code that it couldn't ever be greater than. It always has to be less than in order to stay and open enough students. Okay. Call this defensive programming. What's one of the aspects of defensive programming? Any other questions about this? Yes?
The close and cancel, they are terminating state as well?
That's a good question too. Are closed and cancels terminating states? Well, they are not shown as target symbols, so they're not explicitly terminating states. What we're showing here is that there are no outgoing transitions from them. But the object still exists. If we had a terminating state, it would be tantamount to saying that, perhaps we report the results and then the object disappears. Whereas we're going to keep these objects in existence for other purposes. They're kept with historical record or something like that. Okay? So you don't have to show a terminating state in situations where the object will just exist effectively forever. Any other questions? You'll notice that we're getting lots of questions about these diagrams. We didn't get questions about sequence diagrams the other day. We get questions about state diagrams because they're deeper. There's more in them. There's more analysis you can do with them. And as when you get very complicated state diagrams, you can do a lot of mathematical analysis with these things. Okay. You'll notice, by the way, that there's nothing here that talks about dropping students from courses. So that's an exercise, and that's left till later on. How do you deal with students dropping? If you have students dropping, you're going to have additional transitions as well. Okay, we're going to move on and add a few more pieces of notation to state diagrams. We can have things called activities. Okay, an activity is a computation that takes place while the system is in a state. It's something going on that takes a period of time. Okay, I showed you briefly the concept of an action. The action is a method call that is effectively instantaneous. Okay, so we saw that as create registration. An activity takes a period of time. The system may also take a transition out of a state when an activity occurs. We'll see that when an activity finishes occurring. Okay, so if you start an activity and you say, when we're done with this, exit the state. And you can also force an activity to end in the middle by taking a transition out of a state. And we'll see examples of that too. Okay, so imagine a jukebox application which has two states, proposed selection and music playing, and it goes backwards and forwards. In proposed selection, it's displaying some music selections. People can press buttons and the music will play. And when it's playing, and you can't do anything to stop it from playing. Okay, it will play until completion. And then it will transition back to proposed selection again. So you see this in some music stores where you can actually choose music, listen to it for a while. Now, it turns out that generally speaking, there is a way to get it to change. You can't stand the music it's playing. You press another button and it will play that. This particular diagram here doesn't have that nice feature. You'll have to listen to the ugly music until it finishes, and then you can make another selection. Okay? So we show the activity as a note with in the state with the do keyword, do colon, and then you say what will happen, what activity will go on while you're in the state. And implicitly, unless something else is shown, if we have a transition out of that state back to some other state, that will get taken when the activity ends. That's the implicit assumption. Now we can add more details to show that explicitly, but implicitly that's what would happen here. Questions? We will see more examples of activities in a minute. We're also going to see actions. Now I've shown you the notation slash followed by an action to say when you are on a transition, you can take an action. Okay? We can also take actions in several other circumstances. We can take actions on entry into a state. Okay, so I can say, when we enter a state, no matter where we come from, no matter which incoming arrow, we will do an action. Or I can say, upon exit from a state. So no matter which outgoing arrow we take, we will do a certain action on exit. And so we've got on a transition, which is just labeled with a slash, upon entry, upon exit. We can take actions. And an action, the difference between action and an activity, is an action is considered to take place instantaneously. Its computation is very fast. It's typically setting a variable, maybe sending a message somewhere, but it's something which is not interrupted logically by the ability to do some other event in the middle of it occurring. Okay, it is logically something that is so fast that we don't need to break it down into smaller time units. So let's see a diagram which has some of this stuff. This is a diagram of a garage door opener, in British speak. Got four states. Okay, open and closing, open and closed, triggered by various events. And there is no start state here. So this will just sense which state it's in and will automatically start from that state. So let's imagine that we start in closed state. When you install it and turn it on, it's in closed state. Okay? What this says is that whenever we enter closed state, we will make sure the motor is stopped. So the motor that opens and closes will be stopped. Okay? It guarantees that when we're closed, the motor is stopped. Okay? there's only one outgoing transition, press button. Okay, so it's not going to automatically transition out of this. It's going to wait until it gets a button pressed. So there is a button press that occurs. Presumably it's the owner of the automobile located in the garage that will press the button. It might be a burglar too. It might be the owner of the automobile in his or her car with a radio device that they press a button and as they're driving in and it automatically triggers the opening. Whatever it is, there's a button press and it's all treated the same way by this system. It goes into opening state. And on opening state, on entry to that, the motor runs forwards. So the forwards direction of the motor opens the door. And this keeps occurring, and keeps occurring, and keeps occurring, until we hit opening completed. Okay, this is an event that is triggered by some kind of mechanical sensor that senses that the door is now fully open. That will transition us into open state. Once we enter open state, no matter how we get there, we guarantee that the motor is stopped. We send a signal to a device that says stop motor. Okay, so this is an action. Okay, notice that these are actions. Enter action, stop motor. Enter action, run motor forwards. Enter action, stop motor. So the slash symbol always indicates action. Do indicates activity. Enter slash indicates an entry action. We can also have exit slash indicating an exit action. So the motor is the door is now open, and any press of the button at this time will cause the door to close. So the door will start to move downwards when we press the button, and we're in closing state. And the the mechanism that will actually occur is that when we're in closing state, as soon as we enter that, we run the motor in the reverse direction, which causes the door to close. And now we have two possible transitions. From closing state, if we have press button occurring, okay, while the door is closing, the button can be pressed, and we immediately go to opening state, which says run motor forwards. So we go to that state, the door starts opening again. This is a safety mechanism that says that if we're closing accidentally, we're about to come down on some kid or some car, we can press a button in an emergency and it will reverse the motor, will go back to opening state, and that will run the motor the other direction. Okay? Alternatively, if closing completes successfully, at that point, we enter closed state, we stop the motor, and we wait there. Okay? Question?
Should opening and closing be activities as opposed to actions, because they run and once they stop running, state.
Okay, his question was, shouldn't these be activities? Opening and closing be activities? The answer is yes, you could model them as activities. Okay? It depends on the system. Here what I'm modeling is a simple control system for a door which doesn't, it basically sends a signal to the hardware. It just sends a signal saying run forwards, and then it's done. And it sends a signal run in reverse, and it's done. Okay? On the other hand, if this system was actively controlling, playing music, actively computing, well, you know, how do we open this door? Let's figure it out. Let's play the door opening by computing it. That would be an activity. Whereas if it's just sending a signal to the hardware, it's an action. It's instantaneous. Now, if it was an activity, what I would do is I would say enter. I would say do. You know, run motor in reverse, and then I would just simply have a blank transition here that would take us to closed when it's done. But I could still have the press button to take us out and interrupt the activity. Okay, any questions? That was a very good question, by the way. Yes?
Why wouldn't we have opening state or starting state? Because
We could have a start state that would just take us somewhere by default.
wouldn't it be dangerous if we don't have a starting state as per the diagram that you specified?
Yeah, okay. You're right. This could be dangerous because we could start by random chance in closing state, and so somebody's installing the thing, turns the power on, and the door starts closing. Right? That would be bad. You're right. So there's a safety issue here that we should probably have a starting state that says that basically is open or closed. We could define it. We could say when you install this thing, it's open. Okay, and that's the start point. The system won't fire up unless it's in that state. Any other Questions? Good. Okay, another little example. This has got an exit action. This is a partial state diagram of some kind of tape recording device. Okay, now notice I said partial. One of the things you can do in UML is you can draw diagrams to show pieces of a mechanism. So this is showing what happens, for example, if we're recording. Okay, and upon recording, we can get to the end of the tape. Okay, and we can also get to the end of the program. So if this is an automatically programmed, we're recording a certain show that takes place at 9 o'clock on Tuesday night for half an hour. When we get to the end of that, at 9:30, we take the end of program. If we get to the end of tape, a different thing happens. So two events can occur while we're recording. I guess there could be others, like somebody presses stop, but we're not showing that here. We're just showing a part of the mechanism. The purpose of this diagram is to illustrate that I have an exit state, an exit action that says stop. Okay, so we're going to stop the recording process. We're going to withdraw the record heads from the tape medium. Okay, no matter whether we end program or end of tape or any other way of getting out of this state. This is a shortcut. I could have said end of tape / stop, end of program / stop, and press stop button / stop. Okay, I could have said / stop on every one of the outgoing transitions. But if I know that I always want to stop when I exit the state, it not only is shorthand, saves me writing it everywhere, but it's also a bug preventative, right? If I say it as an action here, an exit action, then I guarantee that somebody won't accidentally add an outgoing transition from recording that doesn't stop. Okay? I also see a stop action over here, so end of tape goes to rewinding, and then rewinding goes to wait when we get to the start of the tape, and it triggers a stop as well. Okay, so basically this sends a mechanical signal, stop whatever you're doing to the electronic device, and once we stop rewinding, we just go to wait. So effectively I stop recording, immediately go to rewinding, and then I start rewinding, and I could have an event here that says signal to the hardware to rewind. I could have an entry event. I could add details to this. But the point I wanted to illustrate is this exit action here. Questions? Okay. Let's take a look at a much more sophisticated diagram. And again, in each diagram we're adding a bit more syntax. This is a diagram of an automatic transition. And this is a diagram that has some weaknesses in it. And one of these weaknesses is an exercise in the book that you can take a look at. It's pretty complete. It does most of what we want, but it does have some drawbacks that you can think about. So let's work our way through this. First of all, we have a start state. This says neutral is where we start by default. But you'll notice another start here. This second start is inside this big box. This big box is called a state which contains nested states. Okay? So first, second, and third are nested, what are called substates, inside an outer state. Okay? So really what I have here at the top level is three states. Neutral, reverse, and this big drive state. Okay? Within the drive state, I've got first, second, and third substates that are automatically, the system automatically controls whether I'm in first, second, or third internally. Okay? With the automatic transition, the only thing the humans can do, or the main things the human does, is reverse, neutral, and drive, although we'll see in a minute the human can automatically force it into one of the other substates, because there are other little 1 and 2 buttons we can fiddle with as well on an automatic transmission. Okay, so the concept of nested substate is that while I'm in the drive state, I'm considering myself to be in that state as a whole, but there are lower level states that I can be doing certain details within that higher level state. So I'm driving, but I'm also in 1, 2, or 3 within the driving superstate. Okay? let's walk through it. Start in neutral. What can happen while I'm in neutral? Well, look for the outgoing transitions. You should always walk through state diagrams in this way. You should look for the outgoing transitions and look for the incoming transitions. Outgoing transitions, select first, select drive, select reverse. Those are the three things the driver can do. Let's take reverse first. It's the simplest case. If I select reverse, I go into reverse state. And I'm there until I select neutral. We assume that we move the transmission through a neutral point to get to drive. We can't just shove it from reverse into drive. It's got to go through neutral. Okay, that's what this diagram is assuming. Okay, otherwise we get quite a lurchy drive. We're going backwards and all of a sudden we're lurching forward again. There's a safety mechanism that assumes that we're neutral even for a split second. There is some period of time we're in neutral. Okay? Now, if the driver selects drive, notice that the arrow goes from the boundary of the neutral state to the boundary of the drive state. Okay? So now what we're doing when we go to the boundary of the state is we're saying we don't care what substate you go into. We'll let the state diagram as a whole in that substate take care of what happens now. Okay? So if I go to the boundary of the state, it says I'm in drive. And now let's take a look inside the drive state to see the way that works. It's a separate diagram all of its own. Okay? So within the drive state, my default is to go into first. I have a starting transition into first. Okay? Think of it as a little diagram unto itself. Okay? From first, where can I go? Well, I can't go too many places. I can go, well, we'll see later on that there are 4 places I can go, but there's one obvious one, and that is reach second speed. Okay? This says, if I speed up to a certain point, my transmission should automatically take me to the second gear. Okay? And from there, if I reach third speed, it should automatically take me to the third gear. If I drop below third speed, it should take me back to second. And if I drop below second speed, it should take me back to first. Okay, so that's what happens in automatic transmission. It just chooses what gear you're in automatically by the speed that you're going. Okay. Now, it might be more sophisticated than that. It might take into account the amount of torque that's applied and various other factors as well. But let's just imagine that it's simple and straightforward like this. Okay, so much for that. There are a few other things that we have to look at here, a few other details. The first one is that there's this condition here called drive selected. When you see a condition in square brackets in a state diagram, it's called a guard condition. And a guard condition basically says we're only going to take this transition in response to the event if this condition is true. So we're only going to go into second if the automobile driver has actually selected drive, okay? Because on an automatic transmission, you've got neutral, drive, and then you've got 1, 2 in most cars. So I can select 1, and if I select 1, notice when I'm in neutral, and I select first, I stick in first. Okay, I'm in first, substate here, but the user hasn't selected the drive. The user has selected first, and to force the car to stay in that gear. And therefore, even though I reach second speed, this condition is false, and I will not go into second gear. So I stuck in first gear. Same thing happens if I'm in second. I can manually select second, okay, from neutral, and I will stay there. I won't go down to first because drive has to be selected to take this transition automatically, and I won't go to third because again drive has to be selected to do that. Okay, so drive selected is a guard condition that's gating all of these internal transitions here. It's preventing the transitions from occurring unless drive is actually manually selected by the driver, which is the normal case, but it has to be done. I'm going to take your question when I've finished walking through the rest of it, okay? A few things to notice. If I'm in third and I drop below third speed, I will go back to second. Okay? There's no guard condition on that. And the reason why is because there is no other thing that can occur. There is no way that I could automatically that I could manually get to third. I can only get to third automatically because there is typically on most cars there is no on an automatic transmission. There's no way to manually select third. It's only selected automatically. And so under those circumstances, gee, this really doesn't want to stay on, does it? Under those circumstances, I really cannot. There's no way I need to have that guard condition drive selected. Okay, it's not necessary. Now, so remember, we can out of neutral we can go into drive, which takes us to the automatic mode where the system will select. We can go into manually into first. We can go manually into second with select first and select second respectively. At any point in time, I can go to neutral. This select neutral arrow from the boundary of the drive state to the neutral state says if the driver at any point in time selects neutral, I will, whatever I'm doing, I will jump into neutral. I'll get out of this drive state and jump into neutral right away. Doesn't come from first, doesn't come from second, doesn't come from third. It says from any of those substates, I'm going to go to neutral. And the transition from the boundary, the very bottom, from the boundary of the drive state up into first, as a substate, says no matter what I'm doing in the drive state, if I manually select first, let's say I'm in drive, I manually select first, I force myself into first state. Same thing, select second from the boundary of the drive state at the bottom. If I manually select second, I force myself into second state. No matter whether I was in first or third, I will now be in second. Okay? Any questions about this? You had a question, has it been answered?
Sort of, but you said that the only way to get to third is by having drive selected. And so, since drive is selected anyway to get to third, shouldn't it already be on drive selected exit third? So
yeah, the condition, you know the condition is true. Okay? You don't have to have a condition that says if drive select, if drop below third speed and drive selected, you just have to say, if we're there in third and we drop below third speed, we know the drive is selected because we couldn't have got there otherwise. So we don't have to add it again. We don't have to have that if condition a second time because we know the only way we could have got there to start with is if drive was selected.
what if your car was turned off when you were in third?
What if your car was turned off when you were in third? That isn't handled here. Some cars will refuse to start up unless you're in neutral or drive or whatever. I drive a standards, so I can't. I'd have to analyze what happens if I put it in third and start the ignition. But hang on a second. If I put it in second and start the ignition, you can't put a car in third. I don't, unless fancy cars have a way of doing it. But certainly, automatics I've driven have only first and second selected. Any other questions? Yeah.
You actually assume that we can go from neutral to second. But
I assume we can go from neutral to second. Right. That is the select second. Yes.
yeah, but we can't do that. We always have to pass by first.
You always have to pass, as you're sliding the thing, you always have to pass by first. Okay, now that's a good point. And so this design is perhaps not mapping to the way typical cars actually work. Maybe it should only be select first and select second could only come from first. Right now, so I'm saying select second could come from everywhere, whereas this is saying in that case select second could only come from first. In which case I could simplify the diagram a bit. You're right. Any other observations about this? That's the first time somebody's pointed that one out, but that's actually an interesting one. There are a number of other observations you can make about this diagram. Okay, I'm going to leave them as an exercise for you to think about. There's a few things that probably ought to be added to this to make it more complete. All right? I'll let you puzzle over it. One of the things to remember is that as we get into any level of sophistication, you have to be very careful to make sure you get these things right. This is a safety-critical system, right? Okay? So it needs to be analyzed very carefully. In fact, what you would do with this kind of system is you would do a formal mathematical analysis of what the possible states could be and what could happen in each state. you'd use an area of software engineering called formal methods, which uses a lot of discrete math and logic to analyze the possibilities and make sure there are actually no dangerous situations. It's still actually relatively simple. You can get into diagrams that have hundreds of states, and you really have to do a job with automatic analysis tools under those circumstances. This was controlling a nuclear plant, for example. You want to make sure that you can't have certain situations that cause a meltdown. And that's exactly how nuclear plants are controlled. They're controlled by state diagrams. Okay. And you can see we've already asked a whole bunch of questions about state diagrams. There's subtleties in them. They're not things which, you're obviously going to get right. And that's why I say, it's a very important area to understand properly. It's an area that we will go into in more depth in subsequent software engineering courses. The diagram earlier on about the student course registration, okay, didn't use nested substates. This diagram on slide 32 does. So it is basically taking the previous concept and adding nested substates to it. It's the same, basically doing the same kind of thing. So whereas before I had not enough students request to register, create registration, and enough students had the same transition on it, if I put a box around these two, okay, call it the open state, I can then put this, I can prevent the repetitive or the redundant duplication of this transition, and just put it as a reflexive transition around the outer open state. Previously I had cancel going from not enough students to cancelled and from enough students to cancelled. If I put a box around it, I can just have one arrow from the outer box, one cancel arrow from the outer box to cancelled. So it allows me to simplify my diagrams and have fewer transitions. I don't have to have the duplicate ones. I can just have them in one place. You'll notice that closed registration still goes from the inner substate, because what happens in closed registration is different depending on whether I'm in not enough students or whether I'm in enough students. Another thing I'm showing here, just as a matter of interest, is an activity, unregistered students in the cancel state. That's a new thing that I'm adding to illustrate the point. That what I might do as soon as I hit cancelled is go through this process. It takes some time of unregistering each of the students that was in there. Okay, any questions about this? So these outer states, or the process of nesting substates, is often a very powerful way to simplify a state diagram. If you see two states or more states which have similar transitions, think, is there a way to group them together so that I can only have one transition from an outer superstate? It's often a very powerful way to make diagrams simpler. Okay, so that brings us to an end of our activity diagrams, end of our state diagrams for now. However, activity diagrams are basically an extension of the concept of state diagrams. They have much of the same notation with some slightly different semantics. And so we're going to treat them as a special case. In fact, in UML 1 at least, they're considered a special case of state diagrams. There's some proposals in UML 2 to give them enough distinction so they aren't considered special cases of state diagrams. But for now they are. So activity diagrams are like state diagrams in many ways. The big difference is that the transitions are caused primarily by internal events. In state diagrams, transitions are primarily caused by external events, i.e. button pressing, events happening, door finishing the closing process, things like that. Whereas in activity diagrams, it's the end of a computation, i.e. the end of an activity, that is the dominant thing. And we use them to model flow of work, okay, or perhaps interaction between use cases. We'll see that in a few minutes. and very often several classes working together as they do various things and interact with each other. Okay? And one of the powerful things about them is their ability to show concurrency. We've seen concurrency before. Concurrency is pretty key and critical in client-server systems that we've seen, because we have these tasks that work concurrently in parallel with each other. So let's take a look at a particular activity diagram. You'll notice we have the start state, or the start activity. We have the terminating ones. We have conditions controlling things. Okay, this transition will only be taken if this condition is true. Okay, and now we have these horizontal lines. They can be shown vertically. These bars, as they're called. Bars are used for synchronization. Let's walk through the diagram, it'll become clear. Okay, so this is a diagram of the process of registering in a course as done by the system. Okay, so the system receives a course registration request. It then has two logical things to do. It has, first of all, or not necessarily first of all, it has to verify the prerequisites. It has to make sure this student is authorized to take the course. Okay. Secondly, it has to verify that the course is in full. And it doesn't actually matter which of these is done first. I could verify the course not full, and then check to see if the student has authorization. Or I could check authorization and then verify the course is in full. Which one is done first is somewhat, they're independent of each other. Basically, at the end of the day, I've got to have done both things, and then if they're both true, I can go ahead and register, right? And so we can model this as they can be done in parallel. This horizontal bar means these things are now going to be independently processed. It might be that in practice, when we implement this, we serialize them. We do one first or the other first. But from the process of modeling and analyzing, we're going to say, we don't care. You do either one first. It doesn't matter. Or, if you have parallel processing available, you can do them at the same time. Alright? And so, the horizontal bar, or the bar, represents a split of control. We'll go down the left branch and we'll go down the right branch independently. If we go down the left branch, we start checking the prerequisites. And if they're not okay, we check special permission. If that's not okay, we're done. We're out of the diagram. Whole thing terminates. If we check prerequisites and they were okay, we jump down to the next bar. Now the next bar has two incoming arrows. Okay? This is a join condition. We have splits and we have joins. The join says, at this point we're going to wait. We're going to wait. We can't go on until we have flow of control passing to both of the incoming arrows, or all of them if there's more than two. So we have to wait for the verify not full to be done. If that's okay, we get down to the arrow, and by the time we get there, to the bar, by the time we get there, if the other incoming transition to the bar has also been reached, we can then proceed to complete registration, and then we're done. But if verify course not full turned out to be not okay, we just kick out of the entire diagram. Okay? We just quit. Yeah?
What's the point of checking if the prerequisites are there if the course is full? Like, why wouldn't you just check that first because if it's full, there's no point in checking the prerequisites?
You could phrase, what he says is, what's the point of checking the prerequisites are there if the course is full? I could phrase it the other way. What is the point of checking if we're full if we don't have prerequisites? The whole point is that either one can be done first, and that is the entire point here. Okay, you're absolutely right, but both ways of phrasing it make sense, and you've got to choose one or the other. And this diagram is telling us it doesn't really matter which one you do, which order. It might end up being that checking fullness is by far the more efficient one, in which case it might be better to do that first and then do the other one. So you typically do the one that is easiest to do, so that if it turns out to be negative, you can quit without having done the expensive work. But that's a design issue. Okay, it might depend on how this thing is designed internally. And so if we're just specifying high-level specifications, we might not want to specify that in that detail, because we don't know what the computational cost of each of these checks would be until we get down into deeper into design. Any other questions? Okay. Okay, so we've got forks, joins, and rendezvous. I call the fork a split, but they're typically called forks. Forks, joins, and rendezvous. Fork, okay, has one incoming, multiple outgoing. A join has multiple incoming, one outgoing. A rendezvous has multiple incoming, multiple outgoing. Somewhat less common, but also quite useful at times. Okay, so I've just basically explained these various kinds of things. The rendezvous, okay, once all of the incoming transitions occur, then all of the outgoing paths can be taken. That's the concept. Okay, a join, the outgoing transition will be taken when all incoming transitions have occurred. We saw that at the bottom part of the earlier diagram. And the incoming transitions are conceptually in separate threads. Okay, now I can implement the thing by getting rid of the threads at the implementation time, but conceptually at the analysis level, we just imagine them as being separate threads. That's the way to model it. And a wait occurs if at the join until the other transition occurs. So if one transition gets to the join, that bar, that will wait until the other transitions get to the bar, and then we can proceed only. And that wait might be indefinite. And if it is indefinite, that could mean there's a bug in the system. Okay? We typically would want a situation where we get them all to that bar at some point, or else we quit entirely, as we did if we hit any of the end states. And I'm going to show you a concept of swim lanes. Okay, swim lanes are where we show effectively multiple activity diagrams that are going on in different objects at once, where there is some synchronization of their activities using these fork and join bars. Okay, so on one swim lane we have student object and its behavior. Another swim lane we have course section object and its behavior. Okay, so we're starting off in the course section receiving the registration request. Then I hit the fork. The fork is saying, okay, we're going to go out, the student object is going to be given the task of doing some work, and the course section object is going to be given the task of doing the other work. And so I'm taking the same diagram and I'm saying who does what work, which object does what work. Okay, so the student object is now taking care of doing the check prerequisite stuff. And it might reach an end state which has to terminate the entire thing. We have to send a signal back to kill the activity on the other side, but would terminate there. The course section is going to do the verify course not full, and then they will synchronize together. There will be some mechanism by which they will communicate with each other and say, okay, are you done? Am I done? Okay, we're both done. Now course section is going to take control and finish off the process. Complete registration. Now, this is a little bit simplistic. You wouldn't probably implement this kind of complexity with multiple threads doing tasks in such a simple piece of work as registering in a course. But in much more sophisticated systems where you have tasks that take a lot of time and a lot of work, you do have to delegate time-consuming work to different objects and say, okay, you go off do that, you go off do that, you go off do that. And we'll meet after a period of time and when we've all finished our pieces of work, and then we'll be able to continue from there. Okay? So when you have time-consuming work, delegating work to multiple threads and multiple objects can be a powerful way of speeding up the elapsed time to get a job done. And the swim lanes just say who does what. They're called swim lanes because they move down in time. It's a bit like swimming in a swimming pool, 2 lanes in a swimming pool. Question?
How do these objects meet again at the same place? Like
His question is, how do the objects meet again? that requires an implementation mechanism of concurrency primitives of some kind, which we're not going to get into in this course. Okay, there are various things called semaphores and monitors and things, which are subjects of more advanced software engineering courses that allow you to actually deal with the process of controlling this concurrency. Okay, I'm illustrating conceptually the idea now. Later on in another course, you'll pick the details out. A lot of the deep stuff in software engineering comes out of this material and the material in state diagrams, okay, which you'll get to in 2101 and subsequent courses. Any more questions? Okay. So we've seen the diagrammatic notations. I believe one of your assignments is you will be given a little bit of practice in doing one of these things. I think assignment 6. I have to double check that, but I'm pretty sure it's there. There will be exercises done in one of the labs. The TAs will be guiding you through some of these. Okay. Let's talk briefly about how we would implement these things. We talked about implementing class diagrams and particular associations. How do you implement state diagrams? Well, there are a number of ways of doing it. I'm going to show you one way. There are 3 or 4 well-known, well-established ways of implementing state diagrams. I'm going to show you one way that's somewhat simple for this simple case, but wouldn't probably expand and scale well to a very complicated case. But nevertheless, it gives you a concept of how you use variables to store states. Okay, first of all, when are you going to use state diagrams? You're going to use state diagrams in classes or subsystems where you have significant complexity in terms of the behavior of objects. If an object can behave in different ways and you have to carefully understand what behaviors are appropriate at what times, then you need to draw state diagrams. And then if you're drawing state diagrams, you need to implement those diagrams faithfully. Done the diagram, it's got to be implemented that way. The code has got to match the diagram. And the diagrams can help you to create a correct implementation. Okay? And if you don't do the diagram, you might end up with bugs. The diagram can help you work out all the possible cases, and then it becomes straightforward to map the diagram into the code from that point. Okay? They're useful when you have behavior distributed across several use cases. We've seen use cases where you do one thing, another thing to achieve a task. But if the behavior is distributed across use cases in the sense that some use cases will cause you to branch one way in one state, other use cases will cause you to branch another way, and you want to model the entire possible sets of behavior, such as in the automatic transmission where you had use cases to change different gears in different directions. The whole thing comes together in a state diagram. Okay? Sequence diagrams tend to take you through one path. State diagrams show you all the possible paths. That's one way to look at it. Okay, so we're going to model the CourseSection class, which we saw the diagram of a short while back. Okay, the course diagram class is on slide 32, also on an earlier slide, as I said, where we didn't have the nested state. So we have planned, open, not enough students, open, enough students, cancel, closed. Okay? So in planned state, what we want to do is we want to work out the conditions of several variables. We want to create variables that represent the states. One way of doing it is to have one variable that's called state. And that variable has the state you're currently in as the name, and that's it. Depending on what the name of that, what the value of that variable is, you determine what you should do when events occur. Another way of doing things, and what is shown here, is that I actually have several variables together that combine to model the state. Okay? And so I'm going to have closed or cancelled as a variable, and I'm going to have open as a variable. Okay? Closed or cancelled basically is going to model the situation when we're not accepting students, and open is going to model the situation, another situation. And we'll see these in a minute. We'll see what these will become clearer to us in a few seconds. So planned is the very first state we go into. And both these variables are false. Cancelled, okay, is one of the final states we can get into and get stuck into it if we cancel the course. Closed or cancelled is true, and registration size is 0. Okay, so if closed or cancelled is true and we've got nobody registered, then that is the definition. If this condition is true, we're in cancelled state. There's no students in the course, and it's closed or cancelled. Closed, on the other hand, is a different case. Closed means that the course section is either too full or being taught. We're not accepting new students in it. So closed or cancelled is true, okay, meaning we're not accepting new students, and the registration size is greater than 0, so we have some student in the course. Okay, so that's the difference between cancelled and closed. Okay, so these are the two states that were over on the left-hand side of the diagram. Open is this big master state that surrounds not enough students and enough students. And open is simply controlled by the variable. Open is true. Okay, are we in this open or are we not in this open state? Not enough students, which is a substate. Open is true because we're in this superstate. And the registration list size is less than the minimum. And so we'd have to evaluate this. And the other substate, enough students, says open is true, and the registration size is greater than or equal to the minimum. Okay? So these are the conditions that will be true when you're in a state. You can find out what state you're in by testing these various variables or expressions to determine what their values are. And that will allow you to determine what state you're in. Okay? And the transitions that will occur, the methods that will cause us to change transitions will change the values of these expressions. And that will cause us to be in a different state, implicitly. Okay, here's a class diagram that illustrates what we're dealing with. We've seen this diagram before. This is just a recap that tells us that we have CourseSection, and it has RequestToRegister and AddYourRegistration list as methods. Okay, so RequestToRegister is one of these methods, these important ones, that will allow us to change state eventually to being full. GetPrerequisite is something that we might call in that activity diagram we saw earlier on, and AddToSchedule and HasPassCourse will be used in the activity diagram earlier on too. But for the state diagram, RequestToRegister is one of the important ones. We would also presumably have here close and cancel as well. I should have shown them but they are also going to be important. Okay, so some of the code for the CourseSection class then. We have a variable showing the course object. Okay, the many-to-one association, the abstraction occurrence association from the course to the course section. We have a list of registrations. Okay, this is who's registered in the course. And then we have our variables determining the state. The other variables determining the state. Because these ones will determine state too. The registration list, whether it's full or not, will be part of what determines the state. The open variable is Boolean, helps determine state, and the closed or cancelled Boolean also helps determine state. Okay, we have our constructor that is going to set up the course that we're a section of and an empty list. Okay, so when the constructor is called, we're now going to go into planned state. So if you look at things carefully, you'll realize that because open and closed or cancel start out as false, and this new linked list starts out as empty, that is our definition of being in planned state, is those three things. Okay? So we're in planned state. Okay, cancel. To go into cancel state, by using the cancel method, I set open to false. So if I was in open, I'm no longer in open. I set closed or cancel to true, so that I don't go into the state where I'm closed but teaching. I actually want to go to cancel, and I have to call unregistered students to empty the students out, because I said that one of the definitions of being in cancel state is that the list of students is empty. So I've got to empty them out. Okay, so that will pull me into cancel state. You'll notice the difference between planned state and cancel state is that closed or canceled is true. Planned state, closed or canceled is false. But here I'm going to be in closed or canceled true. And I can go to cancel state from pretty well anywhere, even from planned. Okay? The only difference is that I'm setting this closed or canceled to true. Unregistered students would do nothing because there's no students. So what I'm showing here is methods that trigger changes to each state. I'm not going to go through all of them. OpenRegistration says if we're not closed or cancelled, because we must be in planned state, then I'm going to set open to true. It takes me into the open state. And by default, open not enough students because my student list is empty. And I have CloseRegistration doing similar kinds of things. And RequestToRegister. I'll let you look at this code in detail. RequestToRegister is going to add 1 to the number of students, and eventually might take me to closed state. Okay? It says here near the bottom, if registration list size is greater than or equal to course, get maximum, then we're going to go to transition to closed state. So I have to check every time I do this RequestToRegister whether I should transition to the closed state. And there's some more code there. I'm not going to walk through it in detail. I want to just wrap up today quickly by mentioning difficulties and risks in modeling interactions and behavior. The main difficulty is that this is a difficult skill, okay? There are many paths that you can take around state diagrams. You have to learn to read state diagrams by looking at all the outgoing transitions, understanding all the conditions that can occur, understanding all the guard conditions. Get used to it. You will be questions about this on the exam. You will have to interpret these diagrams and understand when a sequence of events occur, where you're going to be, what the consequence of adding a new transition would be, what the consequence of an event would be. Okay? The way to do this, the way to analyze these things is to just get practice with it, okay? And we'll leave the lecture there. We'll start chapter 9 next day.